These data were measured at different path energies on the same instrument from a silver sample. And the two spectra that have been acquired are a silver 3D and a Fermi edge. And the idea is that the silver 3D provides a peak shape, so we can see how the peak shape alters with the path energy, while the Fermi edge is an example of where there's a threshold, where the signal drops to zero in theory after a threshold in energy. A Fermi edge is interesting because it provides a shape that is unusual for XPS data. For a silver 3D, which is more typical of what we would see, we see bell-shaped curves. And these bell-shaped curves are the combination of the photoemission process itself, the broadening due to the instrument, broadening due to the X-ray source, and any thermal broadening that's associated with the temperature of the sample when the measurement was performed. In the case of the Fermi edge, because these spectra are being emitted from a band structure, we see a well-defined step and no peak. This means that at the Fermi edge we have a structure that is just a consequence of the instrumental broadening, the X-ray broadening, and any thermal broadening of the photoemission process. The significance of a Fermi edge to the photoemission process is that this is a way of characterizing the measurement itself as opposed to the photoemission process. And therefore the speed of the drop from signal to no signal, in other words the width of this interval over which this edge can be measured, is a lower limit to the width that we could expect for a photoemission peak. The way a step is characterized is to fit a complementary error function to this step, and then the complementary error function, which is based on a Gaussian, gives us a position and also a width for the step that is associated with the Gaussian that is integrated to form the complementary error function. So if we create a region and we indicate an interval about which the step is well defined, and then we specify the step down background type and allow it to initialize the coefficients. The coefficients are being initialized within this cross-section field here, and these are parameters that are used to fit this complementary error function to these data. And when we press the region button here, then the error function is fitted to the data. This delivers both a full width half maximum and a position. The full width half maximum is a measure of the speed with which this drop occurs. So this is characterizing the energy resolution of a particular measurement. The fact that we have a full width half maximum of 0.43 for this particular edge is related to the fact that these data were measured using a monochromatic X-ray source. And the reason this is significant is because had this been measured using a standard source where the energy distribution of the X-rays would be expected to have a full width half maximum of 0.85 eV, we could not have obtained a full width half maximum for this step of 0.43. A monochromatic source is expected to have an energy distribution with a full width half maximum of about 0.26 eV, and hence we're able to measure a step that is broader than 0.26 eV in width. An alternative to using the step function to characterize an edge is to consider using differentiation to convert this edge into a bell-shaped curve. Differentiation is usually used for Auger data, and hence the inclusion of an option on the spectrum processing dialog window for differentiation, and the predominantly used form of differentiation is Savitzky-Golay quadratic using 5 points. And that is a standard way that Auger data is differentiated so that quantification can proceed using relative sensitivity factors that are peak to peak in origin. Now in this case we'd like to differentiate the step in this signal, and the response to energy is rapid compared to the normal Auger peaks. So what I'm going to do is use a different form of the Savitzky-Golay algorithm to differentiate this peak using a polynomial of degree 6, and I'm going to use 9 data points in order to perform this Savitzky-Golay differentiation. When I press apply, I end up with an inverted peak, and this is because of the negative slope of the Fermi edge. But this is essentially a bell-shaped curve that corresponds to the step that was previously modelled by a complementary error function. Since we have a peak shape, we can now fit these data using the standard component and background model. So if I change the step down background type to say 0 and then introduce a peak, and it's an inverted peak which I'll make a Gaussian peak, and then I say fit, we end up with a peak model that fits these data with a Gaussian peak. So the response of the instrument and the X-ray source and the thermal broadening is reasonably well modelled by a Gaussian, and the Gaussian in this case has a full width half maximum 0.42 eV, so this is similar to the result that was obtained by fitting a complementary error function. There may be slight differences because the fit of the complementary error function also included an offset, whereas in this case it's a fixed 0 background type, and the fit of the Gaussian is relative to this 0 rather than an offset.